Alright, grade 11 chemistry, bit of a non-traditional video today. We're just going to be doing a bunch of practice problems for predicting chemical reactions. We have all of the knowledge and tools that we need to do these practice problems. And I just figure we'll go through a bunch of these practices, and then it'll help you guys out with the predicting chemical reactions worksheet. A few things to keep in mind up here. Ions will keep their charge, so if it's like copper 2, it'll stay copper 2. If it's iron 3, it'll stay iron 3, and so on. CO2 and H2O are very, very common products in these things, especially in decomposition reactions. And when we write a formula, we always put the positive before the negative. So we really want to focus in on those ions and all this stuff that we did in Unit 1. I've written out the reaction types down here, so you can see the synthesis, decomposition, single displacement, double displacement, neutralization, and combustion archetypes, and that'll help us figure out what's going on. So yeah, we'll just start going at these practice problems. We are going to first predict the type of reaction, then we are going to balance it. First we're going to predict the type, then we're going to predict the products, then we're going to balance it. So we have kind of a three-step process here. So I guess one is going to be identify type. 2 is going to be predict products. And 3 is going to be balance. Right. Okay, so let's just get started. We have this first one here, C6H12 plus O2. C6H12. So what does that look like in our heads for what kind of reaction it might be? Well, we've got the oxygen. Which suggests to me combustion, and it is a hydrocarbon. So that's down here. That's the combustion reaction. So we know just by knowledge, right? We just remember this, that this is going to make CO2 and H2O. So there's step one. We identified the type. It was a combustion reaction. Predicting the products for combustion is relatively simple. We know it's CO2 and H2O. Mind you, we are going to learn about complete and incomplete combustion relatively soon, so it's not always going to be that. Now the last piece is just to balance the equation. So combustion reactions actually are relatively easy to balance because we can leave the oxygen for last. It's a good hint to always leave the single element for last, because we can just put whatever number we want there. We have 6 carbons, right? The carbon is going to make our CO2. So if we have 6 of these, we're going to make 6 of these, 6 CO2s. We have 12 hydrogens, and each water takes up 2 of those hydrogens, so we can actually make 6 waters as well, right? Because 6 times 2 is 12. There's 2 hydrogens for every water. So we have 12 of those. Now we just have to figure out how much oxygen we've made. So how much oxygen have we made? We have 12 from here, 12 oxygen from here. We have 6 oxygen from here. Here, that's 18 oxygen. Okay, 18 oxygens. What's O2 on this side? So to get 18 oxygens, we need 9 O2, and so that's our balanced reaction. C6H12 plus 9 O2 makes 6 CO2 plus 6 H2O. So that's our first one. That's done. Let's go to the next one, C4H6 plus O2. Hey, that's another combustion reaction. In this case, though, now we have some different numbers here. So let's just erase these real quick. But the rest of it's going to go the same, right? It's also a combustion reaction. We know it's CO2 and H2O. So we've done part 1. We've identified the type. It's a combustion because we have the O2 and we have a hydrocarbon. This is C4H6. So we have a hydrocarbon. We have oxygen. We are going to make CO2 and H2O. The amount of carbon is going to give us the amount of CO2. So there's 4 of those. Amount of hydrogen. 6 hydrogens can make 3 waters because each water has 2 hydrogens on it. And now we have to figure out how many oxygens we've got. So 6 O2, that's 8 oxygens. 3H2O is 3 oxygens, because this has 2 oxygens for every CO2. This has 1 oxygen for every H2O, and there's 3 of those. So that together is 11 oxygens. 11 oxygens. So what do I do with 11 oxygens? We have O2 on this side. Well, you can actually use fractions, because remember, there's billions and quadrillions of these things in any sample. So and we don't need round numbers. This is like 3 billion, 4 billion. We can have half a billion of something. So this is going to be 11 over 2, right? 11 over 2. Or if you prefer decimals, you can write 5.5, because that's the same thing as 11 over 2. 5.5 times 2 is 11. And you have the same number. If you don't like fractions or decimals, you can just multiply everything by 2. So this would be 2, 11, 8, and 6. That's another way to balance this equation. So that's combustion reactions. I'm not going to do this one. This one's a little bit more annoying because of that extra oxygen on here. It's actually not that much worse. Let's do it. Let's actually set this guy up. We didn't really talk about combustions that have extra things, but C6H10O3 plus O2 makes, we know it's going to make CO2, and we know it's going to make H2O. We know that's going to happen, right? CO2 and H2O. And same concept, right? The carbon gives us our CO2. There's 6 of those. The hydrogen gives us H2O. There's 10 hydrogens. Each H2O needs 2 hydrogens, so that's 5 H2O. Let's do our oxygens. There are 12 oxygens in the CO2, 12 of them, 12. And there are 5 oxygens here, 5 oxygens from the H2O, 12 and 5. So total is 17 oxygens on this side. 17 oxygens on this side. 3 of those oxygens are over here, so we need 14 oxygens with our O2, because 17 minus 3 is 14, which means that we need 7 of these to make it work. So that is balancing some combustion reactions. Those typically are relatively easy to balance because you have this direct, like the carbons make CO2, the hydrogens make H2O, and then you can balance it out with that single reactant, that single oxygen. All right, I'm gonna pause and we'll get to the next one. Here's the next one. So let's look at it for a second, and let's think about what kind of reaction it's going to be. That's our first thing. We have to identify the type of reaction. Here we have magnesium by itself. Here we have iodine by itself. And that, to me, says it's going to be a synthesis because we've got A plus B. It's going to make AB. So the magnesium and the iodine are going to get together. Now magnesium is a metal and iodine is a non-metal, so it's going to be a ionic compound. So what we need to do is figure out what kind of ionic compound it's going to be. So magnesium, we know from our table. Let me get my table out here. There's my table. Here's magnesium right there. Second column. It's going to be 2 plus. Magnesium 2 plus. Iodine down here. Well, second to last column, right? Group 17, going to be a 1 minus. Iodine is a 1 minus. Right? Iodine is a 1 minus. In order to balance it out, I need 2 iodines. So we're going to have magnesium with 2 iodines. So that's magnesium iodide. Please, please, please note that that's not because I have 2 iodides here. It's because the charges of magnesium and iodine match up like that. If this were something like sodium, that wouldn't happen. The sodium would just have a charge of +1. It would be just 1 sodium, 1 iodide on that side. We have to balance it. Okay, so we've predicted the product. It's magnesium iodide with 2 iodines because of the charge balance. Now we have to balance the equation, and wouldn't you know, this is already balanced. Magnesium and iodine. Magnesium iodide, we've got 1 magnesium, 2 iodines, 1 magnesium, 2 iodines. That's okay. That's not going to happen every time for synthesis reactions, but in this case it works out. Okay, we'll go to the next, I'll set up the next one. Here's the next one. This is copper chloride and hydrogen sulfide. What kind of reaction is it going to be? Let's look at it. Easiest way to think about this is to see if we can split it up in any way, because we've got, you know, AB or CD, maybe we've got something in there. There's no O2, so we can take out combustion. There's no OH, so we can take out that. There's more than one reactant, so it's not decomposition. So I think this one, clearly is going to be a double displacement. We've got copper and hydrogen, they're positives. We have chlorine and sulfide, chloride and sulfide, which are negatives. And they're going to swap. But we need to figure out what proportions they're going to swap in. Copper here, we have to figure out its charge. We know that chlorine, because of the periodic table, chlorine over here is a -1. So the chlorine here is a -1. There's two of those. Chlorine -1, chlorine -1. There's two of them because we have this 2 right here. And so we need to figure out what the copper is. There's only one copper to 2 chlorines, so that tells us the copper is a 2+. We know that copper is a 2+. The hydrogen we know is a +1 because there it is up in the top of the periodic table. There's hydrogen. So it's a +1. And the sulfide, being here with oxygen, is a -2. Sulfide is here with oxygen, so -2. Sulfide -2. Now those are going to keep their charge. Please note up here, right? Up here, ions keep their charge. The copper is going to stay copper 2. And the sulfide is going to stay sulfide, S2-, and the hydrogen is going to stay H+, and the chlorine is going to stay Cl-. So what we're going to have is the hydrogen is going to get with the chlorine. Let me change my color here. The hydrogen is going to get with the chlorine 1-to-1, and the copper is going to get with the sulfide. Right? The copper is going to get with the sulfide. So what we predict afterwards is going to be, well, copper is 2, sulfide is 2-, 2+, 2-. So we get copper sulfide plus the hydrogen is going to get the chlorine is just HCl. It's just a 1-to-1 ratio. Which means we end up with an issue, right? We have to balance this now because we have 2 chlorines here and 2 hydrogens. 2 chlorines and 2 hydrogens, but over here we just have 1 hydrogen, 1 chlorine in our molecule, or in our compound. And so we have to balance it. I think it's relatively obvious what has to happen. If we just put a 2 here, we now have our 2 hydrogens, 2 chlorines, 1 copper, 1 sulfur, and it is balanced. So it doesn't always work out perfectly. But yeah, we have to put that too. The reason it's not like H2Cl2 is because ionic compounds always get the lowest ratio. Also, if it was molecular, hydrogen only makes 1 bond and chlorine only makes 1 bond. You can't get H2Cl2. Yeah, so that's that one. We're going to pause and set up the next one. Here's our next one, NaOH and HClO4. It's going to make something. Let's think for a second what kind of reaction it's going to be. Does it match a particular one of these? And one thing that I always look out for is that OH. That OH, right? OH indicates a base most of the time. And so if you check for the hydrogen on the other side, which there is a hydrogen on the other side, you can make water. And water, if you look up here, is a very, 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 very common product. So we know we are going to make water, H2O. We make that water because this OH is going to get with this H. Those two together are going to make water. NaOH. So OH and H makes water. What's left behind then is this Na plus and this thing, ClO4. That's a polyatomic ion. It's called perchlorate. You just have to look it up in the table and you'd find out that it has a charge of -1, or you can predict that because it's just got the 1 hydrogen in front of it. So it's going to be a 1-to-1 ratio as well. It's an ionic compound. We call that a salt. NaClO4. And so we have one hydroxide, 1 hydrogen, 1 perchlorate, 2 hydrogens, and an oxygen, but that's just the H2O from the HHO there, H2O. And then NaClO4 is balanced ionically So that's good. We don't actually need to balance this thing. So that's kind of nice. So I'm going to pause and we'll set up the next one. Next up, we've got this thing, zinc carbonate, zinc 2 carbonate specifically, and heat. Now heat, no matter what Aristotle says, is not an element. So this is just a single thing at the start, and we only have one type of reaction that starts with a single reactant. This is A plus B, this is AB plus C, AB plus CD, HB plus COH. There's only this guy, only the decomposition, so it's going to fall apart. Now there's a problem here in that it's not going to fall apart neatly. And one way to remember this is that guy up there, CO2, is a very common product. This is something we're going to learn soon, that carbonates typically give carbon dioxide when they decompose. And what's left over is actually going to be an oxide, because oxides are very strong as well. It's basically zinc rust. We have to figure out what kind of oxide. So let's actually split this up. Remember that ions will keep their charge. So this is CO3. If we look in your ion table, you'll see that it's a 2 minus. That means the zinc, we have to figure out what kind of zinc it is, because there are multiple kinds of zinc. In this case, this is a 2 minus. There's only one of it. So this is a 2 plus, zinc 2 plus. So we know it's going to make CO2, and we're going to make zinc oxide. So if we combine zinc with oxygen, zinc oxide, oxygen's a 2 minus because of where it is in the table in group 16. 1 zinc to 1 oxygen is just fine. So ZnO, zinc oxide. And that is the reaction that's going to happen here. Balancing, well, 3 oxygens, 1 carbon, 1 zinc, we're good to go. That's fine. If it weren't zinc, if it were, again, sodium or something like that, or aluminum, you'd get a different balancing. Let's go to the next one. Okay, here we have HCl and zinc. So we have HCl, which is a 2-parter, right? H and Cl. And we have zinc just by itself, just zinc. So what is it going to form? What kind of reaction is it going to be, right? Our first thing is identify the type of reaction. We look here, and we have zinc by itself. And so it's going to be a single displacement reaction. What is the zinc going to displace? Well, zinc makes the zinc 2 plus ion. I just get that from my table of ions. There's my zinc 2 plus right down here somewhere. There it is, zinc 2 plus. Zinc 2 plus ion. What's it going to replace? The positive here is going to replace the positive, and the positive comes first in the formula if you saw them first. So it's going to replace the H plus, and this is a Cl minus. So the zinc 2 plus is going to get with the Cl minus, which means we need to balance out the charges here, because it's a 2 plus and this is a minus, and we want it to be neutral. So we need a second Cl. So zinc is going to get with chlorine, make zinc chloride. There's zinc chloride. And then the hydrogen has to be by itself on this side, just the hydrogen by itself. But hydrogen is a Hofbrinkel element, right? If you know your Hofbrinkel, basically everything here, N, O, F, Cl, Br, and I, those ones, and hydrogen, they all make diatomics. So this by itself is going to be H2. Right, so we've predicted the products. Got to keep the Hofbrinkel elements in mind. And now the last piece is to balance the equation. Well, the zinc is fine. 1 zinc, 1 zinc. But we have 2 chlorines and 2 hydrogens on this side, and 1 chlorine and 1 hydrogen on this side. I think the balancing comes out pretty easy there. Just throw a 2 in front of HCl. There's 2 HCls. That, of course, multiplies the H and the Cl, so we're good on this side for the 2 chlorines and the 2 hydrogens. That's that one. Let's move on to the next one. Let's have a look at this one. Think about it for a second. What kind of reaction is going to be? Can we split it up in any meaningful way? Does it match one of these archetypes? And that should be probably long enough. If it's not, just pause the video. We have two parts here. This is calcium chloride, right? Calcium chloride. This is potassium carbonate, because that's one of our polyatomics that we have to remember. Let's look at our ions here. Calcium makes a 2+. I know that because it's in group 2. Right? If you're ever in doubt, just check that. Potassium makes a 1+. Potassium plus. Chlorine, Cl-, makes a minus. There's 2 of those because it's matching the 2+ for the calcium. And carbonate makes a 2-, just because that's what carbonate does. Now these things are, it's a double displacement. That's our type of reaction because they're just going to swap, right? The 2 positives are going to swap maybe, or the 2 negatives are going to swap if you want to think about it that way. Never swap, you know, a positive and a negative. Don't tell me it's going to be calcium, you know, calcium, potassium. That's just not going to happen. 2 positives aren't going to get together. So the potassium is going to get with the chlorine 1-to-1 because it's K+ and Cl-. That's going to be KCl. Right, they're just going to swap. And the calcium is going to get with the carbonate 2+, 2-, so 1-to-1 ratio, CaCO3. CaCO3. So you got KCl, CaCO3. Now we have to balance. We have 2 chlorines and 2 potassiums, 1 calcium, 1 carbonate. So calcium and carbonate is okay. And once again, we're just going to double the potassium and the chloride by multiplying that thing by 2. And it's balanced. That's a good one. Double displacements are usually relatively easy to balance. Right, we're going to move on to the next one. Here's our next one, K plus Cl2. So we just have a single element here. No way to split that into 2. Single element here. No way to split that into 2. So we have a single thing and a single thing. The only thing that matches is synthesis. So this is going to synthesize, and this is a metal, and this is a non-metal. So it's going to become an ionic compound. If it's going to become an ionic compound, we have to figure out what ions it's going to make. Potassium makes potassium plus. You just get that from the table. Chlorine makes chlorine minus. Same thing. Get that from the table. So this has to make KCl. KCl. That's our product because that's what we're predicting our product. 1-to-1 ratio because the charges have to balance. This is what I was talking about earlier, where it's not going to make KCl2 because then you have 2 negatives for your 1 positive. That's not going to get together in that ratio. So, and now we have to balance it. We have 2 chlorines on this side. Let's just do this holistically. 2 chlorines on this side. We need 2 chlorines on this side. We're going to multiply this by 2. Multiply it by 2. Remember that multiplies the whole thing by 2. If we put a big number in front of here, it multiplies the whole thing by 2. So now we have 2 potassiums. If there's 2 potassiums here, we can balance it putting 2 potassiums on that side. Synthesis is also relatively simple to balance because you've got those single elements that can balance out quite nicely. So moving on to the next one. Okay, here's the next one. Look at it. Let's think for a second. What kind of reaction could it possibly be? And remember that what we've been thinking is, how do we split these things up? Can we split them up? So can we split this up? Well, yeah, sure. There's a metal and a non-metal here, barium and chlorine. So we can split that up to barium and chloride, the ions. Here we have K, which is potassium, and PO4 should ring a bell. That's phosphate. So we can split it there. And because they're ionic, we can split them into ions. Barium 2+, chlorine minus, potassium plus, PO4 3-, because that's the charge on potassium. If you're in doubt, check your table. And now they're going to get together. So the potassium, they're going to swap, right? The positive potassium is going to give up the negative chlorine. This kind of reminds me of like that FOIL stuff in math. First outside, inside, last, except we're just doing the outside and the inside. The potassium is going to get with the chlorine. That's a 1-to-1 ratio, so that's fine. We'll just write KCl. But this barium is a 2+, has to get with potassium, which is a 3-. So if barium gets with potassium, we can do the crisscross thing. A lot of people like the crisscross thing to show that we're going to have barium 3, potassium 2. Potassium, what am I talking about? Phosphate. Barium 3, phosphate 2. So we need 3 bariums and 2 phosphates. 3 bariums, 2 phosphates. And that is our products over here. We've predicted our products. Now we have to balance it. This balancing is going to be kind of interesting. If we need 3 bariums on this side, we only have 1 barium on this side. Well, let's put a 3 over here. See what happens. Reminder, that multiplies everything. Now we have 6 chlorines. So we have, that's fine. If we have 6 chlorines, we need 6 of these, right? Because that's our 6 chlorines on this side. 3 times Cl2 is 6 chlorines. 6 times Cl, 6 chlorines. That's 6 potassiums. 6 potassiums. We have 3 potassiums on this side, so we multiply this by 2. Right. And when we multiply that by 2, we get 2 phosphates as well. 2 phosphates, and there's our PO4 too. We have our 2 phosphates on this side. So it's 3, 2, 6, and nothing. So yeah, double displacements can get a bit interesting when you have to swap the ions and work out what kind of products you're going to get, especially when you get this kind of thing with polyatomic products. Well, I think we've got enough time to do one more, and then there'll be a half-hour video, so we'll do one more. Yeah, let's do this one, Ca plus AgCl. So Ca plus AgCl. What's it going to make? Well, let's look at our ideas down here. We have calcium starting single. We've got this ionic compound over here. So you can imagine it's going to be a single displacement. Now that's going to be ionic, so we need to figure out these ions. Calcium makes a 2+, silver makes a 1+, and chlorine makes a 1-. What is going to swap with what? Well, the positive is going to swap with the positive. So calcium is going to be over here. And when calcium meets chlorine, right, we're going to need 2 chlorines to match the 1 calcium. So it's going to be CaCl2. And we're just going to have elemental silver on the other side. Just elemental silver left over on the other side. Now we have to balance because we have 2 chlorines here, but only 1 chlorine here. So to make that work, we need 2 of these, 2 AgCl. And now we have 2 silvers. Remember that this multiplies the whole thing. So we put a 2 here, and now we're balanced. Ca plus 2 AgCl makes 2 Ag. Hey, you know what? We've got time for one more, and I've got just the one to do. This one looks fun. So it's lithium and nitrogen, just elemental lithium and elemental nitrogen. So we have a single thing and a single thing. The only thing that matches is this synthesis reaction, this synthesis. We're identifying the type as a synthesis, which means these things are going to get together. Now lithium is a metal and nitrogen is a non-metal. It's going to be ionic. You might be noticing a trend here. There's a lot of ionic compounds and predicting ionic compounds. This is why we worked so heavily on it in the Unit 1 when we talked about a lot of ionic compounds. Lithium, we have to figure out its charge. Makes a charge of +1 because we just look at our table. Nitrogen, if we look at its charge, when it's nitride, it's going to make a 3-. Right? It's over here. There's nitrogen in the row 15. It's going to make a charge of 3-. So to make lithium match with nitrogen, we need 3 lithiums. 3 lithiums to match our 3- on our nitrogen. So that's going to make Li3N. Li3N. So how do we balance this? Well, I mean, this is N2. This is N2. There's only 1 nitrogen on this side, so I think the natural thing would be to put a 2 here. to here. Now the nitrogens are balanced, right? And then if I, now I'm multiplying the whole thing because that's how the big numbers work, that's how the coefficients work. So 2 times 3 lithiums is 6 lithiums. So we need 6 lithiums on this side. And now the thing is balanced. So that's one way to balance it. If you want to get a little bit clever with it, you could also say, oh, you know what, I've got 3 lithiums. I'm going to make 3 lithiums. I've got 1 nitrogen, but I've got 2 here. I can just put a 0.5 there. I can put half of a billion nitrogens, half of a trillion nitrogens to balance it out. So that would also be an acceptable answer. In terms of ratio, it's exactly the same. 3, 0.5, and 1 versus 6, 1, and 2 is the same ratio. So, yeah. So there's a bunch of practice problems. I have no idea how many we just did, but it was a lot. And we'll be doing a whole bunch more in class today. So, yeah, thanks.